All right, welcome everyone. Welcome to the last week, first afternoon session. Hope everyone had a good break over lunch. My name is Steve Chong. I'm from just down the road at Harvard University. I'm delighted to be talking to you this week about language-based security, which is my area of research. And I'm thrilled to be here at OPLSS. Very thankful to the organizers for organizing it, for inviting me. I was a student here at OPLSS exactly 20 years ago. Back in 2004. I think that was maybe the third iteration of it. And just chatting with some students over lunch, it's been great to hear how much is still the same. 2 really intense but enjoyable weeks with way too much information thrown at you, but a lot of fun times with a lot of excellent people. Okay, so some of you might be familiar with Shark Week, where, for those who aren't, it's an exciting week filled with watching a whole lot of sharks and information about sharks. I'm honored to be here this week in what I would like to call Steve Week, where we have myself, Steve Zandwick, Steve Holtzen. This, by the way, was me asking ChatGPT to come up with a logo for Steve Week. Kind of did okay. Almost spelled Steve correctly here. And I gave it the pictures of the 3 of us, and it didn't do a bad job. I see Steve Holtzen's coffee mug is still there, although I'm a little freaked out by the wide-eyed, blue-eyed stare that all of us have. And of course, I'm actually really thrilled to be here with Ali as well. So I asked ChatGPT to come up with a logo for a great sitcom called Steves and Ali. And this is what I came up with, which I was pretty thrilled about, although somehow Steve Zandwick turned into a lovable grandfather figure. And okay, I don't want to spread any rumors, but I will say Steve was actually a lecturer when I was here 20 years ago at OPLSS. And finally, I just wanted to thank Steve Holtzen, who was kind enough to swap sessions with me and take the 9 a.m. class for me this morning, which not only allowed me to sleep in, thank you, but more importantly, let me get to a PhD student's qualifying exam this morning. So and the student thanks Steve immensely, as do I. Okay, so what I'm actually here to talk about is language-based security. But before I start getting into that, I want to talk with you about formal methods for security. Now, formal methods for security are really about modeling computer systems in order to understand and enforce security guarantees. So let me break this down a little more. We have some actual computer system, right? A real computer that's running some software, doing some stuff. It is really complex. It is too hard for us to actually reason about. What we do instead is we come up with a model of that system, some simplified version of it. Now, using this model, what we're able to do is reason about the computer system. That is, we're able to use the model to do things like specify what we mean by security. That is what it is we're actually trying to achieve. We're able to maybe, ideally, prove that the system satisfies that notion of security, or maybe if it doesn't, find some behavior of the system that violates our security property. But then we don't just want to keep it up there in theory land, up there in the models. What we want to do is take the results of our reasoning about the model of the system and bring it back down to the actual computer system. And this might be, for example, techniques to enforce our notion of security in the real computer system, or mechanisms that we've designed to defend against attacks, and so on. So I'll be coming back to this diagram probably a few times in the lectures, but it's really helpful to think about this idea of the real computer system, our model, reasoning about the model, but then bringing it back to the system that we care about. Now, there's a lot of approaches for modeling, for reasoning about these computational entities, using logic, using mathematics. The key point is that they enable us, what they should do is enable us to draw reliable conclusions about the behavior of the system. There are different degrees of rigor with which we can apply the modeling. How much of the computer system are we actually trying to model? This really is, that modeling aspect really is more of an art, a craft, than it is a science. Einstein is allegedly said to have, a good model is one that contains everything it needs and nothing more, or something along those lines. Similar to Occam's razor, and a whole bunch of other people have sort of said the same thing. That the whole point of a good model is that it allows us to reason what we want to reason about and it ignores the extraneous details. We're going to be seeing that crop up in a few different ways over the series of lectures. Now, we model computer systems for a number of reasons. To reason about correctness, to reason about performance. What we're interested in here is security. Now, security is often described as making sure that bad things don't happen. And I want to distinguish this idea of security from the idea of functional correctness. Functional correctness is very important in systems, and it's really based around the idea of if we give a system appropriate inputs, is the output of the system appropriate for the intended design or behavior of the system? Is the output correct? Security, by contrast, is in some ways a broader question. What are the things we're trying to avoid, and how do we make sure that we avoid them? Now, there's a lot of different aspects to security. Authentication, authority, confidentiality, integrity, availability. We're going to be, later on in this lecture, looking at a bunch of these to give an overview. But I want to emphasize that we're going to be focused on security in these lectures. Now, when we think about using formal methods to reason about security, there's a number of good things that come out. First of all, we can hopefully come up with a clear and explicit statement of what we mean by security. That is, it's not okay for us to just wave our hands and say, the system is secure, right? We actually need to be clear about the bad things that we're trying to avoid, for example. And having formal methods forces us to actually go through that process and say, well, what is the theorem that I'm trying to prove? What is the thing that I'm actually trying to achieve? Yes, question?
Just going back to that difference between functional correctness and security, is it like just that the security properties are kind of phrased in the negative, like bad things we don't want to happen versus like the
That's a great question. How do we end up phrasing security properties, and how do they look different to functional properties? Just hold that in mind for midway through next lecture. And we'll be, as in between now and then, we'll both be talking about different notions of security or different aspects of security, as well as seeing a whole lot of example definitions. And so that might help sort of explain it. At the moment, this is the sort of intuition to think about is when we think about the security of a system, it's not just thinking about when I give it the inputs, does it give me the correct answer? Does it sort the list correctly? That's an important aspect of the system. But with respect to security, it might be, what if I don't give it a list? What if I give it something else, some other sort of data? What is the behavior of the system going to be? Is it suddenly going to give me access to parts of the system that it shouldn't, for example? Okay. Thanks for the question. And by the way, please feel free to raise your hand, or if I don't see your hand, just speak up. If you have any questions now or throughout my lectures. Okay, so these formal methods force us to be clear about what we're trying to achieve. They also typically force us to be clear about what our assumptions are with respect to who might be a threat to the system, and what the goals of those attackers or adversaries are. So this can lead to some clarity and insight in what we are able to achieve, and also importantly, what we might not be able to achieve once we make those assumptions clear. But to be honest with you, one of the key points of using formal methods for security is that hopefully it leads to proofs of security. So that is up to the assumptions of the model and up to our assumptions of the abilities of an adversary. What we hope to be able to do is the guarantee that the computer system is secure, even against attacks that have not yet been invented. That is secure against entire classes of attacks. Now, by contrast, sometimes the way that security unfolds in practice is that a vulnerability is discovered, maybe because there is an attack on a system. And then the developers, maintainers of that system, look at that attack or that vulnerability, think hard, come up with a patch to the system that maybe rules out that attack, maybe rules out a few similar attacks as well. But there might be other attacks that we haven't thought of yet. that attackers haven't thought of yet. How do we know whether our system is immune to those attacks? Yes, question.
But isn't there a difference between constructing a proof of security for the model that you construct versus the implementation?
Is there a difference between a proof of security in the model and actually securing a real system? Absolutely. And this is one of the things that I want to talk about with respect to using formal methods for computer security. So the key thing here is this caveat, up to the assumptions of the model. So that is, we're proving something in the model, but then we want to bring it back to the real system. And the extent to which a proof or a technique or an idea that you've used to reason about or enforce or prove security in the model applies to the real system is going to depend on the assumptions you've made about that model, the assumptions you've made about the abilities of the adversary, and so on. Right? So there is definitely this important asterisk on any security guarantee that you prove. It's going to be up to the assumptions of the model. Nonetheless, actually going through that process of modeling, of being clear about what you're trying to achieve and what your assumptions are, helps you figure out whether those assumptions are reasonable or not. Versus, let me try and write code that does the right thing as far as I can figure out. Right? That is, in many ways, no guarantee at all, or guaranteed up to only the limited computational ability of me as a programmer. Okay, so these are some of the advantages of formal methods, but there are some disadvantages. As we just discussed, security guarantees are only as good as the model. Also, even though we are required to precisely say what we mean by security, that precise statement might be really difficult to understand. Right? It might be complex. It might require some sophisticated mathematics in order to be clear and unambiguous about the security guarantee we're trying to achieve. And also, actually using these formal methods can be really difficult. It can be expensive in terms of, to be honest, human capital, of humans being able to apply these ideas that you all as advanced students are learning about right now, and being able to apply that to the development of real systems can be incredibly challenging. Okay, so that's formal methods for security. But I'm actually here to talk about language-based security. So the connection with these is that the use of programming language ideas and techniques is actually a really good fit for a lot of these ideas about formal methods for security. So let's dig into why that is. First of all, programming languages has a rich tradition of coming up with models of programming languages. So the lambda calculus, pi calculus, labeled transition systems, and so on. And it turns out that these models of programming languages also are good models of computer systems. There you can model a computer system by expressing a program, a simple calculus. And think about that as being the computer system. So that's great. Programming languages help us with this part of the diagram, modeling a computer system. And of course, as you've been working on and learning about, programming languages also have a whole lot of really fantastic techniques for reasoning about programs, for proving properties about programs, entire classes of programs, and so on. Those techniques for, say, proving the world-typeness of a system also translate into reasoning about security properties. Yeah, question at the back.
So, as an example, would something like a lambda term be a model of a real computer system?
Well, if you think about a lambda term as being, a program, let's say it's doing something. Let's say it's, sorting a list expressed as, nested pairs. That is a model of a program running on a real system that takes as input a list and sorts it, right? Is it a good model? Depends what it is that you want to reason about. But nonetheless, the idea that we can use programming languages to model computer systems, use our techniques to reason about these models of computer systems, and then, to be honest with you, to close the loop, to the enforcement mechanisms that we use in programming languages. So for example, type systems, other static analyses, dynamic analyses, reference monitors, all these kinds of things that we can think about at the programming languages level. Well, we actually use programming languages to implement real computer systems. So a lot of the time, these theoretical ideas, these ideas in a language, in a model of a language, actually translate into real language tools that we use to produce actual executable systems. And that, in many ways, covers this other part, bringing this idea about reasoning about a model back into enforcement mechanisms for the real computer system. Okay, so these are some of the reasons why programming languages is a great fit for this formal methods approach to security. There's also a related aspect, which is that many aspects of security actually rely on the correctness of application code. But when we actually execute a system, we're not really executing that source code. Right? There's a whole lot of compilation going on. There's a whole lot of lower levels of abstraction in the operating system, the instruction set architecture, the microarchitecture, and so on, so that the real computer system is actually running on something that's quite different to the execution model given by, let's say, an imperative, a calculus for a simple imperative language. And so what that means is that if the execution of a system itself doesn't obey the semantics of the source program, then reasoning about the security of the source program is not that useful. So think here about a buffer overflow. Right? If you have a buffer overflow in a system that can end up injecting arbitrary code into the system, it's really hard to reason about what your source program is going to do, because arbitrary data inserted, arbitrary code inserted via the buffer overflow is not going to conform to the source language semantics. But fortunately, within the programming languages community, we also have techniques for enforcing these language abstractions at varying levels of lower level abstractions. And I'll be touching on that in my fourth lecture today. So in that sense, techniques to enforce language semantics, to enforce language abstractions, also fall into this idea of language-based security, whereby enforcing these abstractions from the language level all the way down, or as far down as we can, that's helping us take our reasoning about the model and actually apply it in a useful way to the real system. Any more questions at the moment? Okay. What I'd like to do briefly is give you a quick case study to talk about these ideas of modeling, reasoning about the model, and enforcement mechanisms. It's going to be an area called non-interference. So the idea here is that we have a computer system that's handling a whole lot of information of varying degrees of sensitivity. So you might think here about what's known as a military multi-level security system, an MLS system, where maybe there's different data labeled with nuclear confidential, so confidential information about nuclear program, signals, top secrets, and so on. Or we might think about something more common like a web application. Let's say Facebook, which has different users. And those different users, the restrictions on their information vary from user to user. My data should only be seen by me and people that I'm friends with. Another user might allow people to see their friends and everyone and all members of the public to see certain parts of their data. Right? So the idea is that we have a computer system that deals with data that has different restrictions on it, different sensitivity. The key idea behind non-interference is that we want to make sure that a user or an adversary doesn't learn information inappropriately. Now, I'm going to be going into a lot more depth the next lecture about making this more formal and more precise. But this is the intuition at the moment, okay? That a user should not learn information inappropriately. All right. So that's the real system that we care about. Let's say a web app with different users. Let's think about coming up with a model of this computer system that might give us some traction. So we're going to consider a very simplified setting where we only have two levels of, two security levels, low and high. You can think about low information as being public, anyone is allowed to see it, and high information is secret. We want to restrict it to only a few users. So diagrammatically, you can think about it as we have some system that's going to be taking input. We have several users. One of them is allowed to see secret information. They are the good guy, hence the angel wings. And an adversary, a user who should not be allowed to see that secret information. The system takes some inputs. Some of it is high or secret. Some of it is low, public information. The system does some stuff, whatever it might happen to be, and produces some output. Some of that output is marked as high security, secret information, should only be learnt by the appropriate people. Other information is low or public, that can be learnt by anybody. Okay? So that's one simplification, only two security levels, high and low. Now in terms of the computer system, let's actually model that with a simple imperative language, the IMP calculus that some of you might have come across. So here's the syntax for IMP. The idea is that we have just a few simple commands: skip, assignment of integer arithmetic expressions into program variables, sequence, so command C1 followed by C2, if statements, and while loops. If statements and while loops use Boolean expressions, which are either true, false, or comparing to arithmetic expressions. Okay. Hands up if this is familiar. You've seen something like this.
What does skip do?
What is what, sorry?
What does skip do?
Skip is a no-op. It does nothing.
Okay.
Great, so pretty much everybody had seen it. If we look at the semantics for IMP, is this also familiar to people? Pretty much everybody. Large step operational semantics. Fantastic, thank you. You're going to help me not run over, which I understand is pretty much a tradition of OPLSS. Here are the large step semantics for arithmetic expressions, where of course we have an arithmetic expression in a store and the integer to which it evaluates to, expressed using these inference rules. For completeness, here are the operational semantics for Boolean expressions and the operational semantics for commands. Okay, and here we see our skip command is a no-op. Executing skip starting from store sigma terminates with the final store of sigma. It does nothing. It doesn't modify the store at all. Just picking out another one to show you arithmetic assignment. X is assigned A in store sigma. First of all, we evaluate arithmetic expression A using store sigma to n, and then the final store is that same store sigma, except that program variable X is now updated to the value of n, the result of evaluating A. Any questions about these? I appreciate that throwing up inference rules in general, for a general audience, is assuming a lot, but everyone seems pretty familiar with it. Yeah, question?
The plus rule on the last slide, right?
Yes, moving backwards to show the rule for plus.
So if A1 modifies the store, that's not seen in A2?
So the question is, what if the arithmetic expression modifies the store? So this calculus, the syntax is very carefully chosen so that arithmetic expressions are pure. They do not modify the store. There is no assignment or any other side effect, even non-termination side effects in arithmetic expressions. Cool. Thanks for the question. Okay, moving forward again. Okay, so that is the full and complete semantics of the IMP calculus. The security condition that we care about, non-interference. So the idea is that we're going to say the inputs to our system are the store just before the program executes, and our outputs to the system is going to be the final store. right? The store that we have after our command, which is a model for the computer system, finishes executing. We're going to designate some of the variables as being low security variables, right? So those are the public inputs, and in the final store, they're going to be the public outputs. And some of the variables are going to be high, or secret inputs and secret outputs. And we're going to assume that we have some context gamma that's a function from variables to low or high, indicating what the security level is of those inputs and outputs. Okay. We're almost there. We're going to define a relation on stores, a low equivalence relation, and say that store sigma 1 is low equivalent to sigma 2 if for all of the low variables, that is for all of the variables x such that gamma x is low, sigma 1 and sigma 2 agree on the value for that variable x. So that is, if sigma 1 and sigma 2 are low equivalent, they are exactly equal on all the low variables. Okay, so with this in hand, we can now come up with a definition for non-interference. We're going to say that a command C is non-interfering if, for all stores sigma 1, sigma 2, if sigma 1 and sigma 2 are low equivalent, and when we execute C in sigma 1 and we get sigma 1 prime, and execute that same command C with store sigma 2 and get sigma 2 prime, then sigma prime 1, sigma prime 2 are low equivalent. So to give this in words, what it's saying is that if we start off with low equivalent inputs, right? So we have two executions of the system where the low inputs are exactly the same, but the high inputs, the secret inputs, might differ. If the program executes and terminates, then the output, those final stores, agree on the value of the low outputs, of the low variables. Okay? All right, we're going to see some examples. Actually, let's see some examples now, and then we'll come back and critique this, this definition. Okay, so do we feel that we have the basic idea of this definition, non-interference? Great. So let's look at some example programs. Let's suppose that our context is saying that the program variable x is secret, is high. Program variable y is low or public. Let's take a look at the program y is assigned x plus 42. So is this program secure? That is, does it satisfy non-interference? Hands up if you think it satisfies it. Hands up if you think it doesn't. Okay, people's intuition is good. This does not satisfy non-interference, right? If x is a secret value, the final value of y is going to reveal a whole lot of information about that secret input, right? So that violates non-interference. What about the following program? Same context gamma. X is assigned x plus y is assigned y plus 42. Hands up if you think it satisfies non-interference. Hands up if you think it does not satisfy non-interference. Hands up if you need more sleep and caffeine. Yeah, quite a few. Okay. Well, the majority of the class was correct. This satisfies non-interference, right? In that x is secret information, and if you think about the final value of y, it doesn't depend in any way on x. Somebody learning the initial and final value of y doesn't learn anything about the initial value of x. Okay, what about this program? A little more complicated. If x is greater than 0, then y is assigned 1, else y is assigned 0. Non-interfering? Not non-interfering, so insecure? All right, people's intuition is fantastic. This is, in fact, insecure, right? The final value of y is going to reveal information about the initial value of x, even though there's no direct assignment from x into y. Okay? So this is kind of really interesting. The definition of non-interference here depends on what the program does, not how it does it. And that's kind of emphasized with this program right here. Right? This program is semantically exactly the same as this other one. And so it in fact is also insecure. It doesn't satisfy non-interference because it's computing the exact same program as this one, just with different syntax. All right. Now let's test your intuition a little more. What about this program? While x is greater than 0, do skip. Okay.
Depends on if you can measure the time of execution.
Well, we had the definition of non-interference on the screen earlier. We'll go back to it in just a moment. Let's take a poll of hands. Hands up if you think it satisfies non-interference. Quite a few. Hands up if you think it does not satisfy non-interference. A few less. Okay. It, in fact, does satisfy non-interference. And this is maybe counterintuitive, right? If you think about sitting down and running this program, and the program fails to terminate, that would reveal to you some information about the initial value. Similarly, this program, also the termination behavior of the program reveals information about the initial value of x, the secret information, but it is, in fact, secure. And on the, sorry, look, yes, question.
Yeah. Doesn't this depend on how you're representing non-termination in your system? Because if you could define it
Yeah.
that way, right?
What I'm going to do now is just move backwards in my slides to show you the definition of non-interference again. So here we have the definition of non-interference. And you'll see what's going on here is that we're using large step operational semantics. And here in our precondition, we required that C executing with sigma 1 terminates with store sigma 1 prime. Similarly for sigma 2. So what I'd like us to do now is let's think about this with respect to this as a model of real computer systems. And we can ask the question, is it a good model or not? Okay, so what are some of the, what are your thoughts about whether this is a good model or not? What is positive about it? What is negative about it? Yeah.
It seems that one negative aspect of this model is your program could leak information while it's running, and then when it terminates, it just wipes its entire, say, memory clean, and now it looks like it's not interfering, when in reality some of that information was lost if you saw the whole program trees.
Great. So your point, so I'm repeating the question to make sure those on Zoom can hear. So your point was that intuitively you say that the program might leak information while it's executing, but before it terminates, it cleans things up. And so what's going on there is that maybe your intuition for what an attacker, what an adversary of the system, of a real computer system, could actually observe while the program is executing is a bit more complex than simply the initial store and the final store. Something like that. You're maybe expecting that, real computer systems are interactive, right? We interact with them. They produce input they accept input as they execute and produce output as it goes along. And we might want to capture that in our model of the system. You're right. This is a very simple model, known as the batch model, where essentially it's only the input, the initial store and the final store that are in essence observable by the attack. So that's one of the ways in which this large step operational semantics for IMP is maybe a poor model of some of the computer systems we care about. Yeah, good point. Other things, other issues in which ways this is a good or a bad model. Yeah.
I mean, like you said, it's really simple, right? So it's really easy to prove that something's not interfering. Whereas if you're trying to reason about, I don't know, the type of X conformation, it's very hard to reason about.
Great. So on the positive side, you're saying that the model is really simple, right? I could present the complete semantics of IMP on a slide and a half. And we were able to communicate this key idea of a security condition of non-interference pretty succinctly, right? One bullet point, good enough for us to actually have intuition to be able to look at slides and think about, is this secure or not? Even though for many of you, it was the first time encountering this notion the semantically based notion of security, of confidentiality. And then, of course, yes? Other question? Yeah.
For low equality machine stores, what if they have different variables in the stores? Like one store has X, the other has Y, but they don't.
All right. So the question was, what if the stores actually have different variables? How do we talk about this idea of low equivalence between stores if they have different domains? So this is actually, again, comes down to the simplicity of this model, where our stores are going to be, let's say, total functions from the set of program variables to integers. And so they essentially, by definition, have the same stores. What I will say is with these things, with interaction, with the idea of different programs or different executions of a programming having different locations, we could incorporate those. They would be more accurate models of our computer system. And as a result, it might be more complex to reason about those models or to state what we mean by the security condition. But on the flip side, it's closer to reality. And so when we want to take the ideas that we're reasoning about in the model and bring them back to our real computer systems, that gap might be less. And the assumptions we've been making between our model and the real world are correspondingly smaller, and maybe the gap is less. We also talked about some of those examples were about termination and the idea that this system, this definition and our model is not capturing the idea of the adversary observing non-termination, which seems like something quite reasonable in practice, right? That they don't observe that it never terminates, at least they observe that execution is taking far, far, far longer than they were expecting. Okay. Great. Let's skip talking about encryption for the moment. Okay. So to give you an idea of where we're going over the course of these 4 lectures, we've kind of talked at a high level about this idea of formal methods for security and why programming languages are a really fantastic fit. What I'm going to be doing over the rest of the lectures, well, the rest of today, I'll actually be giving a bit of a primer on computer security, some of the concepts, some of which will crop up in later parts, and some of which won't. Tomorrow, I'll be talking about, in more detail, about information flow, and specifically talking about the security condition, the definition of non-interference, and thinking about how we can get that definition of security to think about the implications for that with respect to our assumptions about the computer system or our assumptions with respect to the abilities of an attacker. Wednesday, we'll actually talk about enforcement techniques, so how we might go about enforcing non-interference in a variety of ways, and then think about how that feeds back into real computer systems. Then on Thursday, the final day, we'll switch it up a bit and talk about enforcing language abstractions. And before I go any further, I should just mention that a lot of my slides are sloth-themed. I have a 4-year-old whose favorite animal is a sloth at the moment, and so thank you to my son and ChatGPT for coming up with some fun, something to break up the mathematics. Okay, any questions at the moment before we move on to talk about the security primer? Yeah.
I'm not sure if this will make sense, but like, would it be possible to do sort of like to check for non-interference? You break up the program into like steps, and then for each step that you do, you treat that as a separate program, and then you check for non-interference.
That's great. So you're bringing up the idea of how do we figure out whether a program satisfies non-interference, or how do we make sure that a program does in fact satisfy non-interference? And the idea of maybe breaking it up into steps, thinking about each step the computation takes, and if we make sure that every step is somehow okay, maybe the whole execution will be okay. Is that the key idea?
Yeah, maybe that might help avoid the problem of like, you know, if you observe the first and the last state, like it's non-interferent, but maybe halfway through something happens that means something. So instead, like you do this sort of continuously.
That's great. So that is in fact a completely reasonable technique for reasoning about computer systems. You know, it's essentially a form of soundness, right? Let's make sure that every step is doing the right thing, whatever the some appropriate notion of the right thing. And so in many ways what you're leaping forward to is given our definition of security, of non-interference, what are the ways that we might reason about that or enforce it in a model and then ideally in a real system? So yes, that is a way that a number of the proof techniques work. Yeah.
Just speaking of the case that non-interference, can we speak that if the program can prove it has non-interference, it will not leak information from the main channel? Or we'll say if we can calculate the data flow from high variables and low variables, there are no if we do a data analysis, we are saying no dependence from the high variable to low variable.
So this is great. I love that you're connecting with the idea of non-interference and thinking about the ways that we might reason about it. What I'm going to do is put those on hold because you're going to be getting a lot more about non-interference on Tuesday and Wednesdays. We talk about semantic definitions and enforcement techniques. But, so hold those thoughts in mind and maybe we'll cover them. And if not, please ask questions then. Thanks. Yes? Practical systems that use this property. Great question. Non-interference in this simple form is actually generally too restrictive to be useful. We'll talk tomorrow about more useful forms of non-interference. But I will say that the ideas of tracking and controlling information flow within a system, which are really at the core of enforcing these notions of non-interference and similar kinds of guarantees, they are used in practice. In a fun setting, a former PhD student of mine is moved to Facebook and is actually a significant part of their infrastructure is taking ideas from information flow control in order to be able to track how information flows through their system. So I've been thinking very carefully about what are the sort of policies you want to attach to data, how do you attach it, how do you make sure that the appropriate security policy is attached to the data at the appropriate point so you know what restrictions to apply to that data. A lot of it there is actually based on the policies instead of the simple high-low thing are actually based on whether the user is giving consent for various things to happen. For example, for data to be used in advertising, which is a form of, if you will, almost like public information, right? It's less confidential if they're allowed to send it to advertisers to be used to target ads. That is, as far as I know, one of the key, one of the large scale deployments of some of these ideas, but they crop up in a number of settings. There are languages and tools and systems that are designed to, for example, reason about high assurance systems, let's say avionics or control systems, where some of these ideas of non-interference are actually encoded at the source language level to help you reason about the correctness and the security of the code you're writing. But I do agree, this is a really strong security guarantee. And this in some ways gets to this idea that a lot of the time the formal methods that we have are really expensive to deploy and to implement in practice. And so the trade-off between them, about whether we actually use these formal methods to build a system, or whether we do the best we can using, I don't know, red teams and testing and debugging and deploying it and relying on other mechanisms such as lawsuits to, or reversing financial transactions to repair damages. Those are actually very reasonable trade-offs to think about. And I'd say that for a lot of people working in formal methods for security, often a key part of what they're doing, definitely a lot of my research is really about trying to figure out how do we lower the costs of formal methods while improving the value that they can add to the system. And maybe we'll get to the point where it becomes much more commonplace to actually embrace these things, to be clear about the security guarantee we're trying to achieve, to be able to prove these things and have reasons to believe that our proofs actually apply in the real system. But yeah, non-interference is a very strong security property. Thanks. Yeah.
So
another
my
question.
question is, how much flexibility can we have on our attack models? For example, can we have like parametric attacker or something like that?
I'm going to, thanks for the question, talking about what do attack models look like and how can we express them. let me put that on hold because we actually have more content, some of which will address some of these questions. So I'm going to move on and talk about primer for computer security. We'll see how far we get in the next 35 minutes. And then, as I say, we'll be taking some of these ideas and looking at them more concretely with information flow, semantic conditions, and enforcement over the next couple of lectures. Okay. But thanks for the questions and for the interest in this. Okay. I'm going to be covering here in about 30 minutes what we could very easily be doing an entire course on. So to kind of give you some structure for what we're going to be doing, we'll talk first of all about policy and enforcement in trust threat models. And if we have time, talk about some good security principles at the end. So first of all, I want to distinguish policy from enforcement. So the idea of policy is that it is, or sometimes leads to, the security guarantee that we want to achieve in our system. By contrast, enforcement is how we're actually going to achieve that security guarantee. Right? Enforcement is sometimes called the mechanism. You might hear the idea of separating policy, what we're trying to achieve, from mechanism, how we're going to achieve it. The threat model, also known as the adversary model or the attacker model, is really the set of assumptions that we have about the abilities of an attacker, or the motivation or incentive or goals of that attacker with respect to the system. A trusted computing base, or TCB, are the components of the system that are trusted. Now, the goal of what we're trying to do is that, given the assumptions of the threat model, and assuming that the components in the TCB are working correctly, the enforcement mechanism should ensure the desired security guarantee, the desired security policy. Okay, so this is kind of the key thing that we're trying for when we think about security. Yeah?
Can we think of a formal proof for a certified system as an enforcement mechanism?
I'm sorry, can we think about what?
A formal proof for a certified system as an enforcement mechanism?
Yeah, can we think about a formal proof as an enforcement mechanism for a system? Absolutely. Yes, and I'd say the way to think about that is maybe we come up with a type system for our imp calculus, which we'll see in a couple of days. And we can prove the well-typed programs satisfy the definition of security, of, say, non-interference. Right? That's an enforcement mechanism. Right? We're throwing out programs that might be insecure. And so there, the thing that I'd point out is that the enforcement mechanism in that case, the type system, is different from the definition of non-interference, which is the security guarantee we're trying to achieve. Type system, there is a mechanism by which we're trying to achieve it. And there may be other mechanisms by which we can achieve the same security guarantee. Okay. All right. So let's dig into policy a bit more. So there's a couple of definitions of what a policy is. Bishop calls it a security policy is a statement of what is and what is not allowed. Okay, so there we're starting to see things along the lines of behavior we're trying to avoid, what is not allowed by the system. Fred Schneider describes it as security policies legislate behavior by people, computers, executing programs, communication channels, and other system entities capable of taking actions. All those things are often referred to as principles. So the idea of security policies legislate behavior by principles. That's a bit amorphous. So let's actually think specifically about the security of information handled by a system. Now, the core of information security, of specifying policies for information security, is known as CIA. Right? This handy acronym is not actually the Central Intelligence Agency, but it's a great way to remember CIA, which stands for confidentiality, integrity, and availability. So let's go through each of these in turn. The idea of confidentiality is concealing information or resources. So access control mechanisms support confidentiality. Right? So these are mechanisms trying to achieve a policy of confidentiality, of concealing information. So think here about cryptography. Right? Encrypting information is a way of limiting access to it. Only those with the decryption key can access that information. And that's a way of protecting, concealing that data. Same with discretionary access controls, something where the system will check, is this user permitted to access that file? Right? That's a form of, often a form of confidentiality, concealing information or resources. A lot of the time, though, we're concerned not just with restricting access to information, but also with restricting how that information propagates, right? Knowledge of that information, right? So for example, if we have confidential information in a file, yes, access control, who's allowed to access that file might be a key part of keeping that information confidential. But we also want to make sure that even once somebody can access it, they're not spreading that information freely, right? Sending it to all over the interwebs. Okay, sometimes the existence of information itself is confidential. So not just which resources a client is using is confidential, but the fact that the client exists at all might be confidential. So think here about, yes, salary records are probably confidential, but salary records of a spy agency and knowing who the spies are, the existence of those employees themselves are confidential information. Okay, so that's confidentiality. It's the idea of concealing information. Integrity is about the trustworthiness of data or about resources. Integrity is often about preventing inappropriate or unauthorized changes to data or to resources. But it includes things like data integrity, so the content of information, as well as the origin of information. So that is knowing where information came from is a key part to the trustworthiness of that information, the integrity of that information. Think here about knowing whether or not, say, a photograph came from actual camera hardware, and thus the photograph isn't faked or modified. That might be a form of origin integrity. Mechanisms to support integrity policies typically either about preventing unauthorized changes to the data or detecting it after it's happened. So in terms of prevention, think about this as access control. Again, who is allowed to write to this file? By limiting which users can write to the file, we might be trying to ensure the integrity of the contents of that file. By contrast, detection might be about determining when data or resources are no longer trustworthy. Maybe keeping a list of who has modified this file. If you think about, say, the Wikipedia edit log, who has been modifying it? And if there's a lot of modifications happening to a page, this might be a sign that the information on it is less trustworthy or lower integrity than we might like. Interestingly, in a lot of settings, integrity is dual to confidentiality. We'll talk about that with respect to information flow later. But with respect to cryptography, for those who are familiar with it, the idea of public key encryption, where a private key is used to encrypt data that a public key can then be used to decrypt. This is dual to notions of using a public key to sign data. Sorry, I got that around the wrong way. Encryption. Use a public key to encrypt data that can only be decrypted with a private key. By contrast, and that's a way of enforcing confidentiality. right? To make sure that only the holder of the private key is able to read that information. By contrast, or dually, using the secret key to sign data that can then be verified by anyone using the public key, right? That's dual, right? The role of the private key and the public key are in some ways swapped. And we go from enforcing confidentiality policies, restricting who can read or access information, to enforcing integrity policies, being able to prove where information originated from, or at least which key was used to sign information. Okay, confidentiality, integrity, what's the third one? Availability, right? So that's the ability to use information or resources as desired. Now, attacks on availability are often called denial of service attacks. Okay, they're preventing a resource or information from being available. I want to touch briefly on privacy. Privacy is not one of the acronyms, CIA, but you can think about privacy as really being about the confidentiality of personal information. Okay, so I tend to think about privacy as being a subset of privacy policies as being a subset of confidentiality policies, right? They're information specifically about individuals or owned or generated by people. Privacy policies might include the right of individuals to control who is able to access information about them or what information about them is collected in the first place. And privacy often touches on broader societal questions, right? Very quickly moving into laws, regulations, ethics, and beyond technical mechanisms for specifying and enforcing privacy guarantees. All right, kind of going through a laundry list of kinds of policies. Another kind of policy is non-repudiation. This is the idea that a party that took an action is unable to plausibly deny that they did in fact take the action. So the kind of thing that we might be interested in here is, if we think about real life, after signing a document, signing a contract, then you're not able to plausibly deny that you signed the contract, that it was somebody else who forged your signature, for example. Or that when you send a message saying, I don't know, transfer $10,000 from my bank account to this other account, non-repudiation would mean that you couldn't deny that it was you that sent that message. So what is this related to? Confidentiality, integrity, availability. Sorry, was there a question or an answer?
I was just wondering, is there cases when non-repudiation comes in direct conflict with confidentiality?
Hold that thought for about 2 slides. Thank you. But great question. Does non-repudiation come in conflict with confidentiality? So what is non-repudiation about? Is it about the confidentiality of information, integrity of information, availability of information? Integrity? Yeah, I think it's about integrity as well. The idea that that something really did originate, an action, a message, really did originate with a particular party, a particular principle. Let's think about an example here, electronic voting. So the idea here is that let's suppose you're participating in an election using your computer, your phone, your laptop, whatever, to submit your ballot, to submit your vote. Let's think about some desirable properties, security properties for electronic voting. Does anyone have any suggestions? Otherwise, I will start rattling through them. Yeah?
By like not having to go to a polling station that has high availability?
It's the idea that with electronic voting, you don't need to go to a physical polling location. So a benefit might be high availability, or maybe we actually want that as a desirable property of our system. That
We do want people to be able to vote. So high
Right.
availability is also something we want.
Absolutely. That's a great point. Not my first bullet. so I'm not going to show the first bullet, but you're absolutely right. A property that we'd like is that is availability. It is possible for people to vote. Right? Yeah.
Also availability like after the election.
Ooh, availability after the election. So you mean that there is a result announced?
Yes, also, yeah.
Okay, so what were you meaning, sorry, with availability?
Like after the result is announced, you can audit things.
Ah, okay, so after the after the result is announced, that you have some way of checking the result. Is that, so what kind of guarantee is that? You phrased it as availability, that there is a result that is available, but verifying it.
I mean, I would say integrity.
Integrity, yeah. So that was my first bullet, thank you. Verifiability. The idea that the final tally is verifiably correct. And within the electronic voting community, there's actually two different kinds of verifiability, two different flavors that come up. One is individual verifiability, the idea that every voter is able to verify that the ballot they submitted was included in the tally of the final results. And then also the idea of universal verifiability, the idea that anyone can check that all of the votes that were submitted, all the ballots that were submitted were in fact included in the final tally. Only the authorized ones were counted and no votes were changed during counting, right? So yeah, I would phrase this as a form of integrity, right? That you're able to check that the result is in fact correct. Another property that is sometimes considered as known as coercion resistance. And this is the idea that voters cannot be coerced into voting in a particular way. That is, the voter has no way of proving that they voted in a particular way. It's often the electronic voting systems, the models of the security assumptions are that a voter has some private time with a device that they can actually submit their vote, right? Some time when they're not being observed or somebody looking over their shoulder. But assuming that they have that after they voted, they have no way of proving how they voted, so that nobody can force them to vote in a particular way. So what's interesting here is that this is the opposite of non-repudiability, right? This is a form of confidentiality. You want to keep your vote confidential, meaning that you don't actually have any mechanism to prove that you voted a particular way. You want to be able to plausibly deny whichever way you voted. Great, and availability was brought up as the first suggestion. Fantastic. Great, so here we're thinking about the desirable policies for electronic voting, connecting them with these ideas of confidentiality, integrity, and availability, but how they play out in a particular system is going to depend on that specific system. And I've been able to lay these out, the desirable outcomes that we want, the policy, without talking about anything about how we might achieve it in a system. It's separate from the mechanism that we might use to design a system that can achieve these security goals. Yes, question? So to repeat the question, for coercion resistance, might we be, or maybe an additional property might be making sure that people don't vote multiple times? Yes, that is a desirable property, and I'd phrase it as only authorized votes are counted. That if you vote multiple times, maybe that invalidates all the votes, maybe only your first vote counts, maybe only your last vote counts. But there is some clear notion about what is an appropriate vote, and only appropriate votes are included in the final tally. For some systems, this is squared by that actually being one of the techniques you can use to have coercion resistance, the ability to submit multiple votes and to designate fake votes that will definitely not be counted in the final tally, but have a vote that will be, might actually be one of the ways you might achieve coercion resistance. Does that help answer the question? Or yeah, there's a whole bunch of interesting designs which achieve these or some subset of these through a variety of mechanisms with different assumptions about the adversary's ability or or models of the system. Sorry, there were a few more questions. One there.
We talked about non-repudiation as more of an integrity property, but it seems like coercion resistance is a little bit to do more with confidentiality. Would you say that it falls farther on either side of those two?
Great question. Is coercion resistance about integrity or confidentiality? I think in many ways this is about, coercion resistance is phrased here, is really about confidentiality. That a voter cannot be forced to reveal how they voted, or cannot come up with proof to show that they voted in a particular way. And that's really about the voter being able to keep their vote confidential. And non-repudiation is about, as we talked about, is about integrity. And so, yes, sometimes these things might be, some policies might be in conflict with each other, right? It may not be possible to have, let's say, transparency of salary review processes while maintaining appropriate confidentiality about discussions of employees, right? And so this stuff comes up a lot where you do need to make trade-offs. And that notion about what appropriate security policies are typically fall outside the scope of formal methods, right? There's no mathematical theorem we have necessarily to say this is the right policy. Right, thanks for the question. Yes?
Is coercion resistance with respect to the party administering the election, like the state, I guess, or with respect to other voters?
Coercion resistance is, well, it's going to come down to the threat model. Who are you concerned about? Are you concerned about the organizers of the election doing it, or are you concerned about other entities? I think a lot of the time with electronic voting, it's often phrased as imagine somebody who's living in the same household who is saying, I want you to vote this way, and trying to force you to vote in a particular way. But of course, you might want to make sure that there is a desirable property that isn't on here might be confidentiality of how a voter votes with respect to the people running the election, right? That the people administering the election have no way of knowing how an individual voter voted, even though we might still want these verifiability guarantees. So this is not an exhaustive list of the desirable security policies. Thanks for bringing that up. Okay. I'm going to skip the non-interference example when we been thinking about how we connect that with notions of confidentiality, integrity, and availability. We'll be touching on non-interference more soon, so I'll leave this for you to think about before then. Because I've got about 12 minutes, and I'd love to get on to some more of some of these security concepts. So moving on to enforcement. Enforcement is, as we talked about, the mechanism by which we ensure a system satisfies a security policy. The good news is we have a whole lot of different kinds of mechanisms that we might be able to use. Cryptography, type systems, as we've discussed, program analyses, language abstractions. So even being able to hide the implementation details of a module might be a way to help us enforce various information security guarantees. There might be patterns or idioms that we use, say escaping SQL strings to try and prevent SQL injection attacks, intrusion detection systems, firewalls, a whole lot of different mechanisms. So that raises the question of what is a good mechanism? When is a mechanism a good one to enforce a policy? In the interest of time, I'll go through some bullet points rather than getting you to generate them. But one good thing about a mechanism would be that it's correct, right? The mechanism actually achieves the desired security policy. Another good property of a mechanism would be that it's hard to get it wrong. So that is that when you have a mechanism in the system, it's the only options you have for deploying it kind of force you to use it in the appropriate way. That is sometimes might mean that it's not optional for a developer to use. We often want that the mechanism can't be bypassed. This is known as complete mediation. Right? And the idea being that if, let's say we have an access control monitor, something that whenever, let's say, a resource such as a file is being accessed, the access control monitor is meant to check, is the current user allowed to access this file? Right? In order for that mechanism to be a good one and actually ensure that only appropriately authorized users can access the file, it means it needs to see every request to access the file. If there's a way of bypassing it, we give up the guarantee that the mechanism might be achieving. We want it to be easy to use, possibly even that the developer doesn't know that it is in place as a mechanism to achieve security. We've already talked about this idea of separating policy from mechanism. That is, separating out what we want to achieve from how we want to achieve it. This is desirable. Some mechanisms don't have that. That the policy that the mechanism achieving is often very tightly coupled with the mechanism itself. So for example, if you sit down and try and think about what exactly is the security property that an access control system on your files is trying to achieve, it's really hard to actually describe that except by talking about the file access control mechanism. We also want the mechanism to be useful. And by useful, it's actually pretty easy to achieve security, right? Just pull out the plug, right? Okay, it's hard to achieve availability if you pull out the plug, but at least you can achieve confidentiality and integrity by a system not doing anything at all. So when we have a mechanism that we want to actually achieve some security policy, we want it to be useful or expressive enough to allow a bunch of programs, a bunch of systems that we actually want to run to accomplish the task. So these desirable properties might actually be in conflict with each other. So being easy to use might actually be in conflict with usefulness. And so an example here would be the unsafe mechanism in Rust, right? Rust type system provides some wonderfully strong guarantees. Right? But in order to be useful, the developer actually needs an escape mechanism, a way to turn it off, right? An unsafe annotation to say that this section of code should not be used for parts of the certain parts of the type system shouldn't apply in unsafe code, right? For non-interference, we've touched on the idea of declassification, of weakening the semantic security guarantee to allow some confidential information to be revealed, right? And so there, the idea of, in order to be useful, we might need to be able to, we might have to violate the mechanism somewhat. Okay, with respect to mechanisms for achieving security policies, a useful thing is what's known as the gold standard. Authentication, authorization, and audit. So a lot of aspects of enforcement actually rely on one or more of these things. It's known as the gold standard because they all begin with AU, which comes from aurum, the Latin name for gold. So let's go through these quickly. Authentication, the idea of authentication is confirming the identity of an entity. It's based on one or more of something that you know. So for example, knowing a password or knowing a decryption key is, or signing key rather, is one of the ways you might authenticate. It might be based on something that you have, right? So a mobile phone. So when, with multi-factor authentication, not only provide a password, but then your bank sends you a text message. And the idea is that you then have to ideally have possession of that mobile phone. It's a little more complicated than that, but we'll go with that for the moment. Hardware authentication devices are a more explicit form of something that you possess as being a way of authenticating who you are. A physical key that you use to open a lock is in many ways the idea of having something, a physical thing, something you have as a way of authenticating yourself. Something that you are is also one of the ways of authenticating. So these are typically biometrics, fingerprints, face IDs on phones, retina scans, things like that. Question?
Does the something you are include like behavior patterns, like the test of your human type authentications?
Ooh, great question. Does behavior patterns, do they count as something you know, something you have, or something you are? That's a good question. I don't know how to categorize that. But I do have, if somebody calls you up, if your phone rings, you answer it, and somebody says, hello, I'm Steve from your bank. We're worried about somebody is hacking into your system. Let's transfer the money out of your account to somewhere safe, right? That's an issue of authentication, right? Somebody called you up, and how do you know that they really are from your bank? So what's a way that you could actually make sure that you were really talking to somebody from your bank? Yes, hang up and call them. What is that? Is that you're trying to authenticate the person at the other end of the, of the phone conversation so that they really are somebody from your bank. What does it fall under? Yeah, it's a bit of a tough one. I agree. I would phrase it as something you have. The idea is that the person at the other end of the line, they are with an organization that has control of that phone number. And if that phone number is a well-publicized one for the bank, right? You went to the website, you looked it up, you looked on the back of your debit card to find the phone number and called that number, then they're kind of controlling the routing of that phone number to somewhere. And that's a much better authentication than, hi, I am Steve from your bank and your name is blah and the last 4 digits of your social security number or something. It might feel like they know something, right? But actually your name and the last 4 digits of your social security number or your whole social security number is pretty relatively public information.
I guess some banks will say that, no staff member will ever ask you for such and such. So I guess if you know that piece of information, then you can sort of anti-authenticate scammers, right? Because they ask for these things. So perhaps it's
Right.
knowledge in some way.
Right. Banks also try and kind of make clear about what their protocols are so that that they will never ask you for your password over the phone and things like that. Yes?
Distributed sense of authentication. Like, if you get a phone call, you have scam likely, that's because, there's some likelihood that it's a scam. Does that fall under one of these things?
That's a good question. If you see scam likely on your phone, I would say that that's a form of non-authentication. It's kind of it's an indication from the phone carrier, or not exactly sure where the categorization comes from, saying that the person at the other end of this line may not be trustworthy. So, yeah, it's a good question. Let me just talk quickly about the other parts of the gold standard. Authorization, the idea that can some requested action proceed? That is the requester authorized to perform the action? Now you'll notice here that we're talking about a principal who is requesting an action. So authorization might rely on authentication. That is, you need to authenticate so that you know who it is that is requesting an action in order for them to be authorized, in order to figure out whether they are authorized to do it. Common mechanisms for authorization include access control mechanisms. So essentially just looking up, for this principal and this requested action, are they permitted to do it? But we also have other mechanisms. Capabilities are actually do not necessarily require authentications. Just the idea that the right to perform an action is having a token to do it. So think here about a movie ticket, right? Possession of the ticket is what gives you authorization to enter the movie theater, right? So that movie ticket is like a capability, a token that authorizes you to do something. Authorization logics are a really rich and interesting area to reason about who is permitted to do what, particularly when in a decentralized setting, different principals can authorize various actions. I want to talk finally about audit. The idea of audit is to record system activity and ideally attribute actions to some principal that's responsible for them. Now, the idea of audit, the idea of being able to record system activity is really to allow us to hold principals accountable. This allows us to enforce security policies by providing incentive for people to follow the policy. So that is, if they violate the policy, there might be consequences, possibly legal ones. The fact that we will identify criminal behavior and prosecute it is a deterrent to help people follow the appropriate policy. But also in some cases, audit can let us retroactively enforce a policy. So think here about recording enough in an audit log so that we can reverse financial transactions that violate various policies. We don't necessarily prevent it at the time, but there's enough information to roll it back and make sure that the policy is retroactively enforced. I do not get to talk about trust, threat model, or some good security principles, but the slides are going to be available. So I'll let you take a look at those things. I'm going to be around all week until the end of Thursday, so if you have questions about anything, feel free to grab me at coffee breaks and meals and things. Thanks very much. Look forward to talking with you all tomorrow.